Our next example is the wave equation. So, the wave equation is the simplest example of a hyperbolic differential equation of second order. So, if x is in Rn and t is the time variable, then the wave equation, so if n equals 1, so x is in Rn and t equals time. So, if n equals 1, then you do it models waves in strings or pipes. If n equals 2, it waves on the surface of water. And if n equals 3, you have waves in optics, acoustics, etc. Okay, so again, so what is the equation? You have d2u by dt square xt minus Laplacian u of xt equal to 0. So, this is, and then u of x0 equals f of x given, and du by dt, because it is second order in t, you need to give two initial conditions of x0 equals g of x. Okay, and Laplace is again the boundary thing, and if you have, you may have boundary conditions if necessary. Okay, so we once again will look at the existence of and uniqueness, etc., of the solution of the wave equation using the theory of semigroups. So, we have the following theorem. So, omega in Rn, bounded open set of class C infinity. We are assuming maximum, so as we do not have to worry about various things, we will have enough regularity. So, f in L2, sorry, H2 of omega intersection H10 of omega and G in H10 of omega. Then there exists a unique solution of d2u by dt square minus Laplacian of u xt minus Laplacian of u xt equal to 0 in omega cross 0 infinity, u of xt equal to 0 on gamma cross 0 infinity, u of x0 equals gx, f of x, x in omega, and du by dt at x0 equals g of x, x in omega. Okay, so this is our basic equation such that u belongs to C of 0 infinity with values in H2 omega intersection H10 of omega, intersection C1 of 0 infinity with values in H10 of omega, intersection C2 of 0 infinity with values in L2 of omega. Further, for all t greater than 0, mod d by dt dot t square 0 omega plus mod u dot t square 0 omega. So, I am taking the L2 norm in the x variable, that is equal to mod g square 0 omega plus mod f square 1 omega. Okay. Then if in addition Fg belong to Hk of omega for all positive integers k, and on gamma we have f equals delta f equals delta jf equals etc. equal to 0 for all j greater equal to 1, and g equals delta g etc. equal to delta j of g equal to etc. equal to 0 for all j greater equal to 1. Then u belongs to C infinity of omega bar cross 0 infinity. Okay. So, this is the proof. So, omega is bounded. So, by Poincaré's inequality, we can consider the inner product uv equals integral grad u dot grad v dx in h10 of. Okay. So, now we set v equal to h10 of omega cross L2 of omega. Okay. So, the inner product, so now u v, so u equals u1 u2, v equals v1 v2. Okay. So, the first components will be in h10. So, this is integral omega grad u1 dot grad v1 dx plus integral omega u2 v2 dx. So, now we set v equals du by dx dt. Then star can be written as du by dt minus v equal to 0 and dv by dt minus Laplacian u equal to 0. So, this standard thing, if you have a second order equation, you write it as a system of first order equations. This is a standard technique which we have. Okay. So, now we will look at domain of A is equal to h2 omega intersection h10 omega for the first component cross h10 of omega, and for any u equals u1 u2 in D of A, we will define A of u equals u2 delta u1. So, this will be in h10 of omega, this will be in L2 of omega, and therefore, that is the space V. So, this belongs to h10 of omega cross L2 of omega, which is equal to V. Okay. So, this is well defined, and now you can star is the same as saying that u dashed of t is equal to A of u. Let us say double star. Okay. You have d by dt of uv, that is u dash of t, and then you have minus of equals A of ut. So, if you take it to the other side, v delta u is nothing but the A of u. Okay. So, where u equals uv now. And then u of 0 is nothing but fg. And you recall we put f and g, we said f is in h2 0 intersection h2 omega intersection h1 0 omega, and g is in h1 0 of omega, and therefore that belongs to d of a. Okay. And then if u is in d of a, so u equals uv, then what is AUU? AUU is integral on omega grad v dot grad u plus integral on omega Laplacian u times v dx, but then this you know u is in h2 instead h1 0, so this is equal to minus integral on omega grad u dot grad v. There are no boundary terms, and therefore this is equal to 0. Now you let h equals h1 h2 and you consider I minus a u equal to h. So what is that equation? So I is u minus v, okay, equals h1, and you have v minus delta u equals h2, and u belongs to h2 into omega intersection h1 0 of omega, and you want v in h1 0 of omega. So does there exist uv such that you have this? So if you add these two equations, you get u minus Laplacian u equals h1 plus h2, okay, and that belongs to L2 of omega. Okay. So then there implies there exists unique u in h1 0 of omega solution, and regularity implies u is in h2 omega. So there exists u in h2 of omega intersection h1 0 of omega such that u minus Laplacian u equals h1 plus h2, and now you said v equal to u minus h1, which will belong to h1 0 of omega, okay. So h equals h1 h2, remember this belongs to h1 0 of omega cross L2 of omega. Okay, so this belongs h1 0 of omega, and therefore we have that uv belongs to d of a, and you have I minus a u equal to h. Okay, and similarly I plus a u equal to h, you can check this, also has a unique solution. So this means that a and minus a are maximal dissipative. And together generate a group of isometries. So if u naught belongs to d of a, okay, then there exists a unique solution and regularity v will be du by dt, okay, and regularity follows from the abstract theory. after the Hilliard theorem, we saw that if u is in D of AK, then u in u naught is in D of AK, then it is all that. So, you notice that what is D of AK here? The set of all uv in V such that u is in hk plus 1 omega, V is in hk of omega, and delta j of u equal to 0 in gamma, 0 less than equal to j less than equal to the integral part of k by 2, and delta j of v equal to 0 on gamma, 0 less than equal to j less than equal to k plus 1 by 2 integral part minus 1. This requires some checking, but then one can show, so one can show this. Okay. So then, so given the conditions you have here, now the fact that you have an isometry tells you that you have the conservation law which I wrote down. This comes from the fact that you have an isometry. Okay, so that is just initial, they are all STs are all isometries, and therefore we have that theorem and the result follows. Okay, so remark, G equal to 0 on gamma necessary, since u equal to 0 on gamma, and that implies that du by dt equal to 0 on gamma for all t. Okay, this is true, and therefore this implies, so this means that G must also be 0 on gamma. And then this relationship dagger is called conservation of energy. And then remark again, since we have a group of isometries, we can solve the backward problem. Namely, u dash t equals au in 0 t and u of t equals u gamma ut in dA, okay, assuming it is in dA, okay, and therefore this problem has a solution, and since you have a group of isometries. So similarly, since we do not, since we have a group, unlike the heat equation where you could not solve it backwards, here you can solve it backwards. Okay, so now just as we saw in the case of the heat equation, let us take omega to be Rn now. Okay, so we have du by d2u by dt of xt minus Laplacian u of xt equal to 0 in Rn cross 0 infinity, u of x0 equals f of x in Rn, and du by dt of x0 equals gx x in Rn. So now let us, I will concentrate on the case n equals 1. Okay. So if you will have d2u by dt square minus d2u by dx square equal to 0. So then if you put x plus t equal to xi, x minus t equal to eta, then you get d2u by d xi d eta equal to 0. This implies that u is equal to f xi plus g eta, okay, and therefore you have u of xt equals capital F of xt, x plus t plus capital G of x minus t. And now if you impose the initial conditions, imply we have the D'Alembert solution u of x t equals 1/2 of f of x plus t plus f of x minus t plus 1/2 integral x minus t to x plus t of g psi d psi. Okay, so this is the solution in. So in the one dimensional case, we can immediately see that wave equation has no smoothing effect. For instance, if you take g equal to 0, then you get u of x t is equal to 1/2 of f of x plus t plus f of x minus t. So the solution is only as smooth as f. Okay, it is not, whereas in the heat equation instantaneously it became a C infinity function. Here if you have this solution does not change at all. And also assume f belongs to C infinity on r minus 0, okay, then this implies u is C infinity on R2 except on the lines x plus t equal to 0 and x minus t equal to 0. So these are called the characteristic curves. So you have here x and here you have t, and then you have a point x naught 0, and then you have these lines here x plus t equal to x minus t equals x naught and x plus t equals x naught. These are the constant lines. So if you have a singularity at this point, the singularity will persist on these things. These are called the characteristic curves. So singularities propagate along characteristic curves. Another important difference between the wave equation and the heat equation is finite speed of propagation of signals. Okay, so this function, if you have unlike the thing, so if u of x t depends only on the values of f and g in the interval x minus t to x plus t. So if you look at the formula, you can see that immediately. It depends on the values of f at x plus t, x minus t, and g on the interval x minus t to x plus t. Nowhere, nothing else depends it. So this is called the domain of dependence. So if you have x and t here and you have a point x t here, then you draw the characteristic curves which pass through these points. So this will be x minus t and this will be x plus t, and then this is called the domain of dependence. Then if F and G have compact support, this implies U of x t also has compact support, though the support expands with t. So, if you had, for instance, F and G are confined supported here, then you will have to take the characteristic curves coming. So, the extreme character, so U of x t will be 0, non-zero only in this region, but that keeps expanding, and therefore you will have the solution is this thing. Now, one can write down explicitly the solution in n equals 3. So, this is called the method of spherical means. And for n equals 2, this is called the Hadamard method of descent, which means you write it for n equals 3 and then you restrict it to the case where it is only 2 dimensional, and one can study the properties of the solution of the wave equation. These are described in the book Topics in Functional Analysis. You can take a look, and more or less the essential properties we have discussed already here, and so one can wind up this section with that.